Right, hello, it's your boy Nick with another ER1010 tutorial. So, a lot of you guys have been asking for question 4 on the mock exam just before the exam on Monday. I'm sorry I didn't upload it on Thursday, but I had some things come up, so here it is today, hopefully on Saturday or Sunday. So, I know a lot of you will be watching this actually on the day of the exam, and so good luck to you guys doing the exam right now, trying to copy what I'm doing. So, question 4 is about torsion. It's one of Rucci's questions. It's actually probably the easiest question on the paper for, 25 marks. For the actual work involved, definitely the best by far. If not, do that one first if you can. So if you're watching this while you're doing it, make sure this is the first one, because it's quickest. I would recommend not doing the last question, question 5, with the one with the footballers, because that's... the amount of work per mark is so much more than this one. So what I'm going to do is walk through this one, see if I can do it quickly. You guys should be able to do it a lot quicker than this because I'm going to spend ages explaining why I'm doing things and all different things. So this question is about a suspension system on model cars. So all the actual diameters are really tiny. That's the key word in there, model cars. And the key component is this torsional spring bar. And the original component is 20mm, 210mm in length, and it's made of steel. So straight away you can just pick out those values. So we've got the original diameter, D1, original is 20 times 10 to the minus 3. No, yeah, meters. Meters, L1 is 210 times 10 to the minus 3. And it's made of steel, which G1 is 80 times 10 to the 9 pascals. Right. It is to be extended by 60mm, so we know we're adding on to the lengths 60 whenever we do another one, so L2 will be this plus 60. And the new torsional bar has to have the same stiffness as the original bar, and they're all made of circles. So this is great, we've done the density of aluminium and steel, but we don't need those yet. So, first off, try and visualize it. We're going to go for just a general drawing. So we know D1 is essentially, looking at it side on, a bar, and then whatever the second bar is going to be that plus 60. And that's going to be our second bar. That's going to be made of either steel or aluminium, depending on the actual text. Look, shining off that. So the first part of this question, so I've just got the exam paper in front of me, is calculate the second mounted area for the original torsional bar. So for the original one, which is great because you're actually given that equation in the exam. Or on Google, I don't know, it's on a computer this year, it's weird. So the second moment of area is actually the polar moment of area because it's a circle. So we know J1, because we're still working with this first bar, is pi d to the 4 over 32. So we already know everything in this. We know what pi is, we know what 32 is, and we know D1. So all we have to do is just plug the numbers in. So that goes straight into pi times 20 times 10 to the minus 3 all over 32, and that's to the 4, which equals 4 all over 32. 1.57 times 10 to the minus 8, which is 15.7 times 10 to the minus 9 meters to the 4. That's got a weird unit. So I think that's 4 marks. So straight away we've done one sum, and that's 4 marks straight away. Pause it, and then I'll just. So hopefully that lightens a bit better. But straight away for 4 marks, we've done one calculation, which is just plugging in one number to one equation, which is given to you on the actual paper. So 4 marks straight away, that's a no-brainer. And the other one, that takes about 5 sums. So we actually know that, and I know that as J1, so I'm going to 15.7 to the minus 9. I'm going to keep that. I'm going to keep all my important numbers up here. So we've got 15.7 times 10 to the minus 9 meters to the 4. That's J1. And stick that in a box. Ugh, that's a horrible box. Meters to the 4. That's a 4-ish. 4-ish. Right. So, I think part 2, it says calculate the stiffness of the original torsional bar. So we're still working with D1, L1, G1, J1. I'm going to be saying stiff and shaft a lot in this video, so if you just bear with it, it's going to be great. Anyone watching? If Andrew's watching that, then great, but whatever. So we've got the stiffness of the original torsional bar. This is probably the only equation you're actually going to have to remember. It's the torsion triple. So the torsion triple is just the messiah of all things twisting shafts. And if you remember it, it's T over J equals tau over R equals G theta over L. And what it wants is the stiffness. And the stiffness actually isn't in here. So I've kind of lied to you, but I've not. So what the stiffness actually is it's this value K. And K is GJ over L. So it's actually to do with the modulus and the twisting and the actual ratios of the thing is all within the length of it. So it's how stiff the bar is while you're twisting it. So as long as you remember this equation for stiffness, we should be good. So best thing is we've also got all the values we need for this. So the stiffness of the original torsional bar, the only things we need is G1, J1 and L1. Luckily I wrote J1 over there. We've got G1, we've got L1, so all we have to do is just plug them all in. So G is, so we've got 80 times 10 to the 9, G1, we're timesing that by 15.7 times 10 to the minus 9, which is great, because then they cancel out. And then we're dividing it by 210 times 10 to the minus 3. So we're expecting kind of a tiny number, so that's K1. So what do we actually get? Uh, 5,980-ish, I think, actual value. 5,984-ish, and that's in newtons, pascals, Newton meter per radian, and that's the stiffness. So another equation, plugging in numbers, another 4 marks, that's great. So now we've got K1, which is 5,984 Newton meters per rad. In this case, radians is a unit. I know I said it kind of wasn't last time. So, hopefully that follows. Don't forget, if you leave a question on YouTube, I can answer it. So, we've still got our torsion triple. I'm going to leave that there, because it's the sire. Can't get rid of it now. Question 3 is, calculate the diameter of the new component where the solid component is manufactured from steel. So, all we need to do is calculate the diameter. So this is great. And what it tells us is the stiffness is the same. So, calculate the diameter of the new component where the solid is manufactured from steel. So we know immediately K1 equals K2. So these values have to stay the same. And the equation for that would be G1, J1 over L1 must equal G2, J2 over L2. Now, straight away, in the question, calculate down to where the new component is manufactured from steel, it tells us it's made from steel. So steel doesn't change in the length or size of it, it still has the same material properties. So straight off we know G1 and G2 are the exact same. So I'm going to move these so I can derive some things. Because that's all we need actually. So we know these are the exact same values. What else do we know? So we actually know L1 and L2, so we know those because that's there and that's just that plus 60. So the only things we don't know is these J values, and what I'm going to do is I'm not going to plug the number in because it's asking for the diameter, and the diameter is actually hidden in this J value. So J is pi d to the 4 over 32, and it's asking us for that diameter. So we're going to have to do some mixing around and actually rearrange that equation for D. Wow. D, stiffness, shafts. This is a great question. If I could monetize it, this wouldn't get it. Okay, so next thing, I'm actually going to plug in the D. So we've got pi d1 to the 4 over 32, and that's on the top, over L1, is equal to pi d2 to the 4 over 32 over L2. So that's actually our second equation. We know that pi is the same on both sides and 32 is the same on both sides. So what we're actually left with, I can come back, is d1 to the 4 over L1 must equal d2 to the 4 over L2. So, what's the next question? So that kind of simplifies the entire thing right down. So pause that derivation, kind of leave that there because I'm going to get rid of it. I'm going to leave that at the bottom there because that's all we're working with. So all we need to do now is just rearrange it. So the one we actually want is this because we know the rest of them. So what we can do is we can just take L2 up there. So we can have d1 to the 4 over L1 times by L2 must equal d2 to the 4. Then just take the fourth root of that side and get rid of that. So then we can work out d2 just by plugging in our numbers. So we've got 20 times 10 to the minus 3 to the power of 4 all over times 210 times 10 to the minus 3, 270 times 10 to the minus 3 because it's just 210 plus 60 as it was last time. And then we're taking the fourth root of that. So 1 over 4 is actually the same as the fourth root. And if I work that out, we should get the value. 10 to the minus 3, not 4. So 10 times 10 to the minus 3 times 270 times 10 to the minus 3. All to the so I get 0.02129 meters. 219, which is no 212. Yeah, 2129. 2129, which is 0.0213 meters, which is 21.3 millimeters, and that'll be D2. So actually, again, we've only used one equation. All we've done is just rearrange it and sub numbers in, and that's another 4 marks. So 12 marks for using 3 equations and plugging in 4 numbers isn't that bad. So we now know that D2 is 0.0213 meters. That's a D, not P. Okay. What's the next question? So, part 4. Look at that. Part 4. A commercial director wishes to calculate the size of a solid circular aluminium component with the same stiffness as the original, but the new length. So, the only thing that's changing here is, well, it says it's made out of aluminium, so G is different for this new component because it's not made of steel anymore. So, we're going to straight away go back to what we know. We're going to bring back our torsion triple, which is T over J, tau over R equals G theta over L. And we're going to look at actually what we've got. So we know from the question, K1 must equal K3, so the stiffness is the same. So for the original bar, we can just write down the equation for stiffness. So we know the stiffness equation from before is G J over L, which is G1, L1. And that must equal, obviously, G3, J3 over L3. So most of it's different now. But we can still work with these things because we know most of the values. We know G for aluminium, we know it for steel, we can calculate J, and we know L. So the only thing we've got to do is calculate the size of it. So, for the original one, we'll have... Well, let's just plug in J first off. So we've got G1 times pi D1 to the 4 over 32 over L1, so bad parenthesis, equals G3 times pi D3 to the 4 32 all over L3. So if we do that, we can kind of work downwards from there. Yes. What's the equation for thingy? Okay, so we're trying to calculate the diameter. So the diameter is in here, so this is what we want. This is the only thing we don't know. So we know G, we know G and L, we know that, we know pi and 32. But similar to the last question, we know that pi is the same on both sides, it doesn't change, and 32 is the same on both sides, so we can cancel that straight away. So the only thing that's left is to rearrange the equation. So if I just make that tidier, so we've got D3 to the 4, D1 to the 4, D1 to the 4, and D3 to the 4. So straight away that's a lot more pleasant to look at. You can kind of see what we need from there. So this is what we're trying to calculate. It's similar to the last question, it's just throwing in some extra numbers to confuse you. This time we've got a different value for the modulus, but I wouldn't worry about it. We already know that it's in the question. I'll look at it when we actually go to plug it in. So we know that because it's there, we know this because it's there, we know that because it's there. We know that because it's in the question, I can read it. We know that because it's 270, just that plus 60. So all we can do is just rearrange it. So what we'll end up with is if we take L over there and G over there, we will end up with D3 to the 4 equals G1 D1 to the 4 over L1 times by L3. Wow. Great job, Nick. L3 over G3. Unfortunately, there's no G6. So we'll just do that. And then the only thing that's left is this 4 again. We can get rid of that and put the entire thing to the 4th root. 4th root. 4th root. And then again, it's just 4 marks for plugging numbers into an equation. So what we've got is, we could actually take that out of the bracket, but it doesn't matter. So we've got, actually no, I need to know what G3 has done. G3 in the question is, alright, that's over here. Oh, I need to do it in total now. G3, it says, is 26 times 10 to the 9 pascals, which is about right for aluminium. It's usually between 26 and 27. So that's it. L3 is just 210 plus the 60 millimeters. So what do we know? We know that, we know that, we know that, we know that, and we know that. 4 marks, just plugging it in again. So what do we get? We get 80 times 10 to the 9 times bracket to the 4, no, to the 1 over 4, which is the 4th root, and I get 0.0282 meters ish. So that's now, which is exactly 28.2 milliliters. Great. So again, another 4 marks straight away. We've almost finished this entire question. I'm not sure how long we've been going for. So we can write that down over here. What's the other colour? Oh, we need 2 red. 2 red now, because we've done green. D3 equals 28.2 millimeters. And that's actually that's the same. 21.3 millimeters. Right, 28.2 millimeters. So we just answered another question. All we do is just plug one equation in, and we're nearly done. Not that many questions left. See, I told you this one would be the easiest one. You didn't believe me. Next question. Right, this is a bit of a wordy one. This is kind of one we have to understand the concept that it's asking for. Okay, so this is going to be a really bad edit because that camera died in the middle, but hopefully it kind of fades through and you can see that. So I think we're on part 5, which is comment on any difference in stress, each case for a reacting standard load. So yeah, this is where we kind of have to understand the concept that it's asking for in order to give a comment on any difference. So have a guess what equation we're going to use. That one. So the torsion triple, the only things we actually need to talk about is talking about the difference in stress, and the stress is included in this bit. So we're actually going to talk about those. We're going to talk about this tau. But in order to do that, we need to talk about it with it reacting to a standard load. So the two we're going to use are these two. So we're going to write out T over J equals tau over R. Right. And then from that we're going to comment on tau, given a change in this. So if we rearrange that, then we've got tau equals T over J times R, which means if we sub everything in, because it's reacting to a standard load, and we're talking about the only difference between all of the shafts is, believe it or not, and I don't mean this as a joke, we're going to comment on the size of the D. So these two change, and we've got D1 as well. So the only thing that's really changing in reaction to this standard load is the size of the D. It gets thicker, it gains girth if you want. This video is not going how I expected. So that's what we're going to comment on. So we're going to rewrite this as tau equals T times R, and that's all over, and I'm going to put it in terms of diameter. So R becomes diameter over 2, because of course it does, and J on the bottom becomes pi d to the 4 over 32. So immediately cancel that off and cancel one of those off. So that becomes a d to the 3. And dividing fractions easy. Pi, flip the dividing fraction, multiply. So this becomes 2. So that then becomes 16. So we've got t over pi d to the 13. So we've got 16 comes up to the top. Yeah, okay, that rearranges. So we've got tau equals t times 16 all over pi times d to the 3. And that's our stress reacting to this load. So the load we're applying is this T, and obviously 16 and pi don't change no matter what the size of the shaft or whichever one we're using, aluminium or steel or whichever. The only thing that's changing, given that T is constant, is this diameter, and that's changing for the first, the second and the third one. So when it says comment on the difference in stress, it's how does this affect this? So as the diameter increases, if you think about this going up, then the maximum shear crest decreases. So if D increases, you get less stress, and vice versa. So if the D decreases, you get more stress. So ironically, you want the bigger one to get less stress. So the takeaway from that is tau is proportional to D cubed. So essentially this is what you can write. Tau is proportional to D cubed, so as this increases, this decreases. So what that's saying is the best one is this third one, because it's got the biggest number. Which means the newer bar has the best capability of bearing with that standard load. We're getting a load from a D and everything. Okay, so just write that down and then talk about how the third bar is the best one. Because of this. So obviously it's got the biggest number, it increases, so we get less stress in the system under this standard load. So as long as you can get to this point, I know I kind of did some flipping around there, but it's just simple division and rearranging. As long as you get to this equation, I'll just remember it. That's the comment you're looking for. And the final question is quite straightforward. If you get over the words of it, it's not that bad. So I'm going to get rid of this. Ironically, we don't even need any of this anymore, I don't think. But we do need to go all the way to the beginning of the question, so that kind of takes some scrolling. Okay. So, calculate the mass of the bar with a different diameter and the mass of an aluminium bar with a diameter. Take the length as 350. So, how are we going to get to mass? Well, mass is, we've got the Love-Heart equation, m over v equals rho. So it's a Love-Heart because the m and the v make a Love-Heart. You didn't get that. So we're actually calculating this. So I can rearrange that. Essentially I can say the mass equals volume times rho. That should be a big V and a, oh god. Right, so we've got a V in a row, and then you might be thinking, where am I going with this? It kind of makes sense. So we know rho. We know the density of the materials is given to us in the question. We can just sub them in later on, but it's easier to just work with symbols all the way down. So the only thing I'm going to split up is here. I'm going to split this V into its components, which is going to be the area and the length times rho. So we've got area, length times rho, and then we can just work down even there, because we know the area is just, well, it works out as the rest of it's just related to R. So working down, we've got area is pi r squared times length times rho, which is great. That's it. We've just got another thing to sub in. Is red visible? Yeah, okay, so we've got red from there. So that's it. So we've got mass equals volume times rho, and then the volume splits into the area and the length times rho, obviously, because we're not losing any density. And then the area itself is pi r squared. And that's it. So we're just going to break this equation. As long as you can get to that point, everything's fine, because you can just plug the rest in. So the first mass, I'm going to call it M1, is pi times, what's our first radius? 16 diameter, 8 times 10 to the minus 3 squared, yes, times by the length, which is 350 times 10 to the minus 3, and that's all times by, what was the density? 8,000. 8,000. Great. So M1 is pi 500. No. That's me not being able to read a calculator. 0.563 kilograms. So 0.563 kilograms, that's straightforward. That's M1. I'm going to change that to MS because that's the steel one, I think. Yes, and then next one, MA. A standing for aluminium, so we just do the exact same thing, use the exact same equation, plug all the numbers in, and this time we're using a different value. So we've got pi times 0. Times 14 times 10 to the minus 3 squared times 350 times, and what's the density of aluminium quoted as? 2,700. So straight away, well, not straight away, we'll plug those numbers in again. All I have to do is change 2 of them. And that's a 14. I get 0.581, so 582 kilograms. And that's it, that's my mass. So from that, we can just deduce that, take the length of both, calculate the mass, well, MS, mass of steel, 0.563 kilograms, and that is, well, an MA is 0.582 kilograms, so therefore MA is bigger than MS. And that's it. Another 5 marks just for splitting up that equation straight away. So if you remember your love heart, remember the love heart, and you should be set for 5 marks on that. So essentially 25 marks just for using 3 equations and plugging the right numbers in, which is why I think it's the easiest question on the paper. So that's a fair chunk of the things. So hopefully that clears up a lot. Hopefully you understand it. If not, you can always go back and watch it. You can always drop a comment on the YouTube thing and I can respond to that. Other than that, if you've got any questions, don't forget to email me. Don't forget to like, share and subscribe, if anything. And hopefully that answers your questions.